So this is the second part of section 2.8 on related rates, and we're going to look at a couple more examples. You can find so many different videos on related rates. There are many different kinds, so the focus today is kind of on the different steps that we talked about from the first part of the section in that video. So here we are, we're standing on a pier, pulling a boat towards us with a rope. So kind of notice what's happening here. So the rope is going this way, it's being pulled, and that also means that the boat is heading this direction. So those are things to think about because it matters in terms of the direction of the rate, like when we think about the rate and what the sign is going to be for the rates. So the rope is being pulled 1 meter per second. The end of the rope is 3 meters above the level it is attached to the boat. How fast is the boat approaching the pier when the rope is 5 meters long? So one important thing to see is that our first step is just to recognize that this is related rates. I write that again because we are going to see optimization in the future, and those are kind of the two big word problems we see in the course, and so being able to distinguish between the two. Now, in the last example with the balloon, I was talking about how a lot of like old school formulas come in, area of a circle, we saw the volume of a sphere, things like that. Another really common thing to see with related rates is some relationship between the sides of a triangle. And so that is the key thing to see with this picture, is that what you have is a triangle that is being created. And once you've seen that, really the next step, if you can create the picture, because there are some different pictures for this, creating the picture, you should think about what sides are moving and what sides are not. So we see that as the boat is being pulled in this direction, this side is moving. So I'm going to call that side X. The rope, as the person is pulling it, is getting shorter. So I'm actually going to call that Z. And then, and the reason I do that is because, well, I'll mention it in a second, but one other piece of information we have is that we have the fact that this side is 3. So that's 3 meters above the level it is attached. So one side is not changing. That height is always going to be 3. That does not change. But the other two sides are changing, and that's why I give them variables, because if it's not changing, it doesn't need to be a variable because it's not changing with respect to time. So the things that are changing, as we already said, is the distance of the boat to the pier, and we called that X, and the length of the rope is also changing, and we called that Z. So what that means is when we think about the rates that we're dealing with a dx dt, that's changing with respect to time, that distance. I guess I don't need that. And dz dt, those are the things that are changing with respect to time. Now, it tells us that we're pulling the rope 1 meter per second. So the important thing to see there is that that means that dz dt is 1. But because as we pull the rope is getting shorter, we want to recognize that that's a negative rate. So if, say, we were letting the boat go and float away, that rope would actually be getting greater. And if that was 1 meter per second, then that would be a positive. So notice the difference between, if the triangle is getting bigger or the triangle is getting smaller. Now dx dt is what we want to find, how fast the boat is approaching the pier when the rope is 5 meters long. So that d what, how fast the boat is approaching, is our dx dt. And so I'll put a question mark there because it's what we're trying to find. So the fourth step, as we talked about, already, is, actually maybe I'll bring it down here, is to find an equation that relates everything. And the key thing to see with the sides of a triangle is you could talk about the area of a triangle. There are other things to see with triangles, but a very popular one is the Pythagorean theorem, the three sides of relating the three sides of a triangle. So way back in the day, you learned that a squared plus b squared equals c squared, where c is the hypotenuse. Ooh, hypotenuse, it's not a great writing, but it's what it is. And then a and b are two of the legs, the other two legs. So what we know from our picture is that x squared plus 3 squared equals z squared. That's the relationship between the three, the related, the things that are related. And then by taking the derivative, we have the related rates. So now we can take the derivative. So that is step number 5, is to take the derivative. And remember, anything that's changing with respect to time needs a d what. So in this case, that's going to be a dx dt and the dz dt. So you're using the chain rule as well as implicit differentiation here to get 2x dx dt. Now, we saw this back in the first video. When we take the derivative of 3 squared, remember 3 squared is just 9. We don't need to write that out. You could have written 9 there, that's fine. No matter what, you want to recognize that the derivative of that is 0. And then we have 2z dz dt. And at this point, the next step is just to plug in everything that we have to find what we don't have. So the only thing I haven't written down, I think, is that we're being told that the rope is 5 meters long at the moment that we want to find out this rate. And so that would be when z equals 5. So we're trying to find dx dt. So one thing to notice is we don't have x. We don't have how the distance from the boat to the pier at this moment. And you might say, well, how are we going to do it? We don't have that value. So another common thing with these Pythagorean theorem is that sometimes you're not given enough information to, like, you know, within the words, and so you have to find what you don't have. So we know that x squared plus 3 squared equals z squared. And we also know that we're trying to find out the situation when z is 5. So that allows us to set up our Pythagorean theorem, which is still true at any moment. And 5 squared is 25, and 3 squared is 9. And that will give us 16. So that tells us that x is plus or minus 4, but we know that the distance can't be negative. So we know that x in that moment is 4. So that allows us to then fill in the value for x. So dx dt. We have z, which is 5, and we're told that dz dt is the -1. So you can see that we basically have, and this is just for time here, or in space, the space that I have. So 8 dx dt equals -10. And so just by doing division there, we're going to have dx dt, and that equals a -10/8, which is a -5/4, which is a -1.25. So I write that as a decimal just to make a little more sense in the context of the problem, but what it tells us is that the boat, because again we found dx dt, which is the change in x over time. The boat is approaching the pier at a rate of -1.25, and it makes sense that it's negative because it's getting shorter, and that's going to be meters per second. So the same units that we have in the problem here, meters per second. And so that's the answer to that problem. So anytime you have something that can create a triangle, there's a lot of examples with like planes that are moving from radar stations and things like that, where you have things heading in like, you know, like a plane moving across from a radar station, and so maybe it's like flying past like this, and so it creates this triangle because you're asking, okay, what's the distance? So you want to kind of recognize when do you see the Pythagorean theorem, because that's another very common thing to see with related rates. So last problem here. So notice we have a triangle here as well, so I wanted to do another one with a triangle because they are quite common, but this one is different, and notice that this one has a theta. So an observer watches a rocket launch from a distance of 2 kilometers. So we already have a lot of the picture here. The angle of elevation is increasing at 3 degrees per second at the instant when theta is 45 degrees. How fast is the rocket climbing at that instant? So we'll follow our steps here. This is related rates, but we do see that we have some aspect of trig, and that's going to be a really important thing here. So a lot of this will come down to what are the things like SOHCAHTOA, because you have the relationship between angles and the sides of a triangle. So we have trig here. So things that are changing in this picture, if you think about this, what's happening is this rocket is going up. You see the arrow here, the rocket is going up. So you have that y of t is changing. You have that as the rocket goes up, this side of this triangle is getting bigger as well and moving, you know, this direction, which is why theta of t is also changing. And so we think about what's changing here, and we have the angle of elevation is changing. Angle of elevation. We have the height of the rocket is changing. Height of the rocket. And we also have that person that's watching it here, that distance to the rocket is also changing. So distance of person to rocket. So all of those sides are changing. We might not need all those sides, but all of those things are changing. So notice what we're being given here. I'm just trying to make sure I have enough space. We are being told that d theta dt, that is the angle of elevation and how it's increasing. Notice it uses the word increasing, so that tells us it's positive. And really, that's all we have right now, but it is asking how fast the rocket is climbing. So that's your dy dt, and that's what we're trying to find here. Now, other things we know is that we know that we have that distance at the bottom that's 2 kilometers, and we know that we're thinking about exactly when theta is 45 degrees. So we do have a little more information as well, but those are not rates. So I'm talking about the rates here. So when we look at this, we're trying to find this dy dt. So notice you have this side, and you have something about this angle. So when you think about having this angle and these two sides, you should think about what trig function you need. So understand that for that theta, you have opposite, and you have something about adjacent, opposite and adjacent. So that should make you think of tangent. So you know that tan of that theta, that angle that you have there, is opposite over adjacent, so y over 2. Now remember, theta is changing with respect to time, and so is y. And so when we take our derivative now, we have to consider that. So we know that the derivative of tan from section 2.4 is secant squared theta, but then we have to multiply that by d theta dt. There you go. So that's a chain rule. So you have to take the derivative of theta, which is d theta dt, since theta is changing with respect to time. Then we have 1/2 times, and then the derivative of y. And since y is changing with respect to time, we need a dy dt. And so then it really is just plugging in values and things like that. But we do have to be kind of smart, because notice that we have like degrees here. And typically we don't see degrees in problems, we see them as radians. And so that's kind of the issue to think about here when we do this. So, so now we'll plug things in. So we have secant squared, and this is going to be, what am I thinking here? We have 45 degrees, because that's our theta. That's coming right here. And d theta dt we know to be 3 degrees. And then we have 1/2, and we're trying to find dy dt. So you can do secant squared of 45 degrees, but basically that's 1 over cosine of 45 degrees squared, cosine of 45 degrees is root 2 over 2. And so then if you square that, so I can do that up here. So the idea here is you have 1 over cosine 45 degrees squared, and that is 1 over, and so cosine is root 2 over 2, cosine of 45. And so that's going to be 1 over 2 over 4, which is 1 over 1/2, which is 2. Okay, pausing. What is wrong here? Hold on. So we have 2 here, so that's 2. Now I can also bring this 2 over, so I'll multiply both sides by 2 because I have a 1/2 there, so multiply both sides by 2, and that'll give me a 2 here, and then I have 3 degrees and dy dt. So that gives us 12 degrees, and that's dy dt. But the issue with this is it's asking how fast the rocket is climbing, and we don't think about distance in terms of degrees. And so the way to do this would then to just be to change it to radians. So to get an answer, we would just change it to how many radians that is. So 12 degrees in terms of radians, we divide by 180 and multiply by pi. So it's that idea of multiplying by 1, taking you way back to early trig. And so that's going to be pi over 15, which is about 0.2. And again, that's just because you wouldn't say the rocket is climbing at 12 degrees because rockets climb in terms of some sort of distance, and our distance is kilometers. So we can now say the rocket is climbing at a rate of 0.2 kilometers per, and it looks like we have seconds, kilometers per second. And that's our answer. So yeah, we have a lot happening here, obviously. And I think really quick, let me just double check. Pi divided by 15. Oh yeah, so it's actually 209. So if I do 2 decimal places, I would actually have 21 here. So let me just do that to give myself 2 decimal places. But you know, just depending on what the question asks. So that's 3 examples from section 2.8, and so make sure to talk about the homework and write on discussions and things like that. What questions you have, because it's a big section, it's important, and every problem's a little bit different.